So this question is asking which quadrant is 30 degrees in. As we take a look at this type of a problem, this is another example of those where you would have already seen this come up in geometry, but many of you have forgotten because it was just kind of touched on. So we bring it back again, and when we talk about quadrants here, we're actually going to nail down which quadrant is which because it's part of our verbiage that we use going through this whole section. We'll be talking about locations of angles on the circle, and one of the ways that we can narrow down the location of an angle is by starting by talking about what quadrant it's in. All right, so in this particular case, it's asking where 30 degrees is. The nice thing is that also gives me an opportunity to remind us about how we measure angles. Where is 0 degrees on the circle?
Right.
It is straight to the right, yes. And when we measure an angle, do we go around clockwise or counterclockwise? Counterclockwise, exactly. So I'm going to start at 0 degrees, and I'm going to go around that way 30 degrees. Now, you hopefully know 90 is up here, so obviously it's going to be somewhere between 0 and 90. It's in this top right quadrant. Specifically, it's going to be right there. But the question is, what do we call this quadrant up here? Is that quadrant number 1, 2, 3, or 4? That is quadrant number 1, yes. You'll notice how we have each of those colored in. Basically, as we're going around the circle, that's the order we're hitting them in. So quadrant 1 is the first one that we pass through, going from 0 degrees. We then go to quadrant 2. Then we end up passing through quadrant 3, and then we pass through quadrant 4. That's why they're numbered that way, because they start at 0 and go counterclockwise from there. It certainly would be useful to have that written down in your notes if you didn't already have that totally memorized, so that you can look back and remind yourself should such questions come up again. And then I want to practice determining which quadrant they're in and also figuring out where certain angles are actually ending up on our picture. So for this one, 135 degrees. Which quadrant is that going to be in?
2.
Now, how can we know? Yes, it is going to be quadrant 2. But how can we know? Well, you know 0 degrees is straight right, 90 degrees is straight up, 180 degrees is straight to the left. Notice 135 is between 90 and 180, so it's got to be somewhere between them. A little side note here to be particular though, it's actually exactly halfway between 90 and 180. So if you're trying to figure out which one should it be closer to, this is actually the one that's right in the middle of them. Okay, 330 degrees.
4.
In which quadrant will that be?
4.
Well, as we go around, we saw where 0, 90, and 180 were. If I went around that further, 270 is straight down. If I kept going around, I'd get over to 360. So notice it's between 270 and 360. That means it's down here. Yes, that is quadrant number 4. Finally, where's 400 degrees? Well, we kept going around, right? Remember, we just saw that 360 degrees is in the same spot as 0 degrees. We can keep adding on. In fact, you can go around this circle over and over and over again, always adding another 360 degrees as you go. So like 360 plus another 90 means the top, after going around once already, that'd be then 450 degrees. You notice the 400, it's between those two. Specifically, it is 40 degrees above the 360. And so yes, it is quadrant number 1. All right, so then the quadrants part, that's something we hadn't talked about yet this year. I next want to take a look at something we were talking about in our last lesson, the side lengths of our special right triangles. I want you to fill in the side lengths of the special right triangles, but first, try to do it without your notes. We can always check the notes here in a moment, but try to fill in each of these pictures, please, without your notes so you can kind of check and see how well you're remembering it so far. All right, so let's see how we've done. In the first triangle over here, it's a 30, 60, 90. Now you notice the hypotenuse is 1. That's the part that's going to make this whole thing a lot easier. And in the 30, 60, 90 triangle, I remember we have side lengths of 1/2 and root 3 over 2. I remember those two always go with a 30, 60, 90. So then the question is just which one goes with which side. And there's actually a few different ways you can know it. One way is 1/2 less than root 3 over 2, or is 1/2 more than root 3 over 2? Well, they're both over 2, right? So it's basically which one's bigger, 1 or the square root of 3? Well, the square root of 1 is 1. It's more than the square root of 1. It's the square root of 3, so that one must be bigger. So you notice the 1/2 is actually less, which means that if my drawing is drawn relatively to scale, and in this case it is, the short side is the 1/2, and the long side is the root 3 over 2. So hopefully those are numbers that you're coming up with, and ideally even getting them located in the right spot. Now for the 45, 45, 90 triangle, again with the hypotenuse of 1, just like our unit circle. This one's kind of nice because it's an isosceles right triangle, meaning those two angles are the same, and therefore those two side lengths are the same. So you actually only have to remember one number in order to know what both of those side lengths are. And what is that one number? The square root of 2 over 2, yes. Now these should already be in your notes from our work yesterday, but if not, you're writing furiously right now so that you do have them in your notes, because they're going to be very useful as we go forward. And these values are so important because these are the ways that we can know sine, cosine, and tangent of some of these same angles that are popping up here. So let's take a look at that for the 45-degree angles. So when you look at sine and cosine of 45 degrees, in this case it's actually pretty easy, because remember, we know that in the unit circle, that is where the hypotenuse is 1, that sine and cosine are basically the x and y coordinates. Well, you'll notice here the x and y coordinates are both the same. How far over and how far up we go are the exact same value. And so what will the sine of 45 degrees be? It's just the root 2 over 2. And the cosine must be the same thing. It must be the square root of 2 over 2. By knowing this picture, we can know those values. Now, we also need to look at the 30, 60, and 90. And here we have to be a little bit more particular, because in the last one I referenced that, of course, we know that sine and cosine correlate to x and y, but we didn't need to know in that case which one was which, because they both were the same. In this case, though, we will need to know which one is which. So this goes back to something we took notes on yesterday. In the unit circle, we can know the coordinates of any point on the unit circle because the x-coordinate is always which? Sine or cosine? Cosine. So it's cosine of the angle, comma, sine of the angle. In other words, cosine is the x-coordinate and sine is the y-coordinate. So as I'm looking at this, then I can already know a bunch of stuff, because my x-coordinate in this picture is 1/2. My y-coordinate in this picture is root 3 over 2. So let's go ahead and use that x-coordinate here, 1/2. X-coordinate, of course, that is cosine. So then that tells me a cosine value. But the question is, which cosine value? Is this the 30 or is this the 60? Well, remember that our triangle there is part of the unit circle picture. If I drew in the unit circle around it, I'd be having my axes going through there, and my circle would be going around the outside like this. So then our central angle is the 60, yes. So then this x-coordinate here correlates to the 60-degree angle. So then we can know that cosine of 60 is 1/2. And what's the sine of 60 going to be then? Well, it's our y-coordinate, the root 3 over 2. Remember, wherever we see one of the sides be 1/2, the other one will always be root 3 over 2, and vice versa. It works the other way too. If one side is root 3 over 2, you know the other one has to be 1/2. And of course, this is assuming that our hypotenuse is 1, which is going to be our typical scenario. Now, that little tidbit of information I gave you and reminded you of, it actually has more significance than you might even think at first. Because I now need to figure out what the sine of 30 degrees is. And I could do it by redrawing my triangle and turning it on its side so that the 30-degree angle was now my central angle, and I could reconstruct it that way. But I don't even have to. Because remember, if one of them is root 3 over 2, what's the other one have to be? 1/2. That also works for those types of pairings. So it works even within both of them being sine between 30 and 60 degrees. So you notice if I know one of the sines is root 3 over 2, I know the other sine is 1/2. Again, it's that 30-60 pair. And so in the same way, I can know that the cosine of 30 degrees is root 3 over 2. And there's just all these kinds of patterns like that that are going to be lurking underneath the surface when it comes to knowing these values. And I do mean knowing these values. So far we know this much of the unit circle, and we've looked at these exact values. And yes, I would recommend that you go ahead and write down this table into your notes. It's a nice way to organize information that we've already been talking about. Tomorrow we're going to be adding a whole nother layer to this. We're going to be extending our angles out throughout the whole circle. And we are going to fill in the sine and the cosine values for the entire circle in these various increments. And we're going to have them memorized by the end of class tomorrow. For now, just write down this table, because basically everything that we do tomorrow, it's all based on this anyway. Now, as you wrote down these notes, one thing might have jumped out to you looking kind of weird, right? Something we haven't looked at so far, at least in this class, and you probably saw last year a little bit in geometry, maybe, maybe not, probably depends on the teacher and such as that. But did you notice this symbol here? Looks like a 0 with a line through it. Well, we don't read that as the 0 with the line through it. It does not mean 0. It actually just represents a variable name, the same as we would use x or something like that. So what actually is it? It's theta. It is the Greek letter theta. The Greek letter theta is used like any other variable, so I could have put x in there, it all would have meant the same thing. It has no special like operation or meaning, it doesn't change anything. But in mathematics, theta is typically used to represent angle measures. And so we'll want to know how to use it and be familiar with using it for that reason. In case you're wondering, why do we always like to go back to Greek letters? Well, a lot of famous mathematicians from the past were Greek, and so they used the Greek letters, and so a lot of mathematicians just kept using the same Greek letters. All right, so we now know that theta is this funky looking 0 with the bar through it, and that's how you draw it. Basically the same as a 0, just draw the horizontal line straight through the middle like that. And you just need to be familiar with using it and seeing it and knowing how to read it as we go forward. And go forward we will, because today we're taking the stuff that we were doing in the past day or two, and we're combining some of the concepts. So, in order to start that, I'd like you to please to go ahead and do this problem. It's very familiar. There's just one little caveat. No calculators. So we start the same way. We make a picture, we label it, we decide what the sides are called. In this case, we have the adjacent and the hypotenuse, and that tells us whether it's sine, cosine, or tangent. Adjacent and hypotenuse are the parts of cosine. And so we do cosine of 60 equals the adjacent, 14, over the hypotenuse, b. And then we're just going to solve it like we normally do. So whether you think of this as multiplying both sides by b, or you write it as cosine of 60 over 1 and then cross multiply, you'll end up with b times cosine of 60 degrees equals 14. Well, of course, we got another step from here. We still need to know what b is, so we're going to divide both sides by the cosine of 60. Now, one little side note, I'm going off on a little tangent here, if you will, bring in tangent in another context. I see this written on a lot of people's papers when we start doing this kind of algebra. I would not like to see this on your paper. Because what this currently means is divide both sides by the operation cosine. We can't divide by an operation. We can't divide by the function cosine. That'd be like saying divide both sides by the square root. Square root of what? Same thing. It has to be cosine of something. And so write that 60 degrees in. And I know you're probably sitting there, yeah, but I know what it means. Yeah, and yet you'll be surprised how many people who know what it means right now, by the time they've done that 100 times, they all of a sudden have themselves convinced that you can divide both sides by cosine. Because they've just taken that shortcut so long, they've started to believe that that is actually what they're doing. So include all the details. All right, so when we do that, we end up with b equals 14 over cosine of 60 degrees. And this is the point where then we would normally reach out and grab our calculators, but I said no calculators on this one. Why? Because we don't need it to know cosine of 60 degrees, right? We already have that. In fact, we already have it in our notes. So I can go ahead and just grab that value that we already know. The cosine of 60 degrees is 1/2. And so b equals 14 over 1/2. Although for a few of you, you just cried a little bit inside because there's a fraction in a fraction. If that happened to you, here's the long explanation about how you deal with it. Because it's not actually that bad. Remember, a fraction is just division. So that's the same thing as 14 divided by 1/2. And in order to do division by a fraction, we multiply by the reciprocal of the fraction. In other words, you change the division to multiplication and you flip the fraction upside down. Always the second fraction. Well, of course, multiplying by 2 over 1 is the same as multiplying by 2. Now, if you looked at it and you said 14 divided by 1/2, oh, that's the same as 14 divided by 2, so it just equals 28. You would be right. And that would be your final answer. So b just equals 28 here. All right, now, in this case, we didn't need to use a calculator. How do we know when we do and don't need to use a calculator then? Well, remember we've taken some notes on these, right? We know that for 30 degrees, 45 degrees, and 60 degrees, we know what the sine and cosine values are of each of those angles. Well, that means that if it's one of those angles that come up in that table, in other words, if it's a value we actually know, then I expect you to give me the exact value. Now, if I gave you something a little different here, cosine of 13 degrees, okay, that's not one we know. And so then you would use the calculator for it. So, use the calculator if we don't know the exact value. Use the exact value if we do. And it's going to be up to you to know which ones we do and don't know. To practice doing this, please now find our missing side length in this diagram. All right, and so again, we start by taking a look at the picture so we can decide if it's going to be sine, cosine, or tangent. In this case, it involves the opposite and the hypotenuse, so that's going to be sine. So we're going to do sine of 60 degrees equals the opposite, which is what we don't know, that's side C, over the hypotenuse, which is 10. And then solve from there. You either multiply both sides now by 10 or make it into a proportion and cross multiply. Either way you do it, you should find that 10 times sine of 60 degrees equals C. This is one of those nice ones where we don't have to do a division after that. We already know what C equals. It's just that now we actually need to get the number. Do we know what sine of 60 is?
Yeah.
Yes. That means we don't break out the calculator. We're going to stick with whatever that number is. So we're going to do 10 times root 3 over 2. Now I know that value from my notes, from my pictures, all that stuff we were talking about at the start. Now it's just a matter of simplifying that. And again, if you have trouble with the fractions, here's your quick reminder. If I'm going to multiply 10 by the fraction, I can just think of the 10 as 10 over 1. And then when we multiply fractions, we multiply straight across the top. and straight across the bottom. And so when we do that, we get 10 root 3 over 2. Can we simplify that any further?
Yes.
Yes, because you'll notice here the 10 over 2 reduces. I can divide them both by 2. And so then that gives me 5 root 3 equals C. That is then as good as I can make that, so that's my final answer. Since I can give the exact answer, I am giving the exact answer. Then on to the next one. Please find the length of side x in this picture. And so you notice the two sides involved are the adjacent and the hypotenuse, so that's how I know to use cosine, because cosine is the only one that involves adjacent and hypotenuse. So do cosine of the angle equals the adjacent over the hypotenuse. We then either multiply both sides by x or set up as a proportion and cross multiply. In this case, we will have to do some division. I'm skipping a step here, but you should end up with 12 over cosine of 30 degrees. Now it comes time to actually knowing what the value is of our answer. So we have to ask ourselves, do we know what cosine of 30 degrees is?
Yes.
Yes, that means we should be able to do this without a calculator. So since I know what the value is, I'm going to plug that in. So we're going to do x equals 12 over, and it happens to be root 3 over 2. Now this one's not quite as pretty as the other ones, but we can still do it. So, again, dividing by the fraction is the same as multiplying by its reciprocal. So I'm going to be doing 12 over 1, because I'm going to look at that as a fraction as well, times the reciprocal of the denominator. So that's going to be 2 over root 3. And so then we can go ahead and do that multiplication. It gives me 24 on top, and it gives me a root 3 on the bottom, which is certainly looking a lot better, but is not actually done. Because, as you may recall from some of our recent practice, we can't leave the square root in the denominator. Remember, we need to rationalize the denominator for this to be in simplest form. And so, to get rid of the root 3 on the bottom, we need to multiply top and bottom of our fraction by the square root of 3. All right, good. Then when we do that, we get 24 root 3 over 3. Are we done?
No.
Nope. We're not, because even that can simplify some. And so, we're going to do so. So, divide top and bottom by 3 in this particular case, and you end up with 8 root 3. And now, you're done with that one. All right, so having done those practices, I think it's time to take a look at these types of problems from maybe a different angle. Please find the missing angle. There are two ways that you might have approached this problem, and they both will get you to the correct answer, but I hope by the end you'll see that one is probably preferable to the other. One way is we figure out that we're going to call this side the opposite and this side the adjacent, and so therefore we're going to be using tangent. So we do tangent of theta equals 36 over 36. I'm going to go ahead and simplify that. So that's going to be tangent of theta equals 1. And then if I want to solve that for theta, I'm going to do inverse tangent of both sides. And so theta is going to equal inverse tangent of 1, which then you could plug into your calculator and get the answer, which you also could have gotten right off the bat if you had noticed. What type of triangle is this? Isosceles, because these two side lengths are the same. Therefore, these two angles are the same, and it therefore must be a 45, 45, 90 triangle. Either way will get you there, but certainly if you recognize that pattern at the start and are like, wait, if the legs are the same, I know what this is, you can use that. All right, then this is the last one we're going to do together. Please find this missing angle. All right, so in order to do this one, we figure out that from our angle, the opposite and the hypotenuse are the two sides that we know. So then I can do sine of theta equals the opposite, which is the root 3, over the hypotenuse, which is 2. And then, yes, you could go ahead and take inverse sine of both sides, and then you could do the square root of 3 divided by 2 and then inverse sine of that. Or you could say root 3 over 2 seems like a very familiar number. In fact, that's one that shows up in our table of values, and it's one that we actually know. Sine of what equals root 3 over 2? 60. I know that from my notes. So I didn't even have to do the inverse sine thing. Now, if you did, it would still get you the same number, but isn't it much easier to not have to?